this PowerPoint some, and like I told you, I do use the canned PowerPoints because they're good. I mean, why recreate everything? But I'll go in here and there and add my own stuff in, and I like to write over the tops of these too. So if you want to take notes, that would be great. If you don't, it's up to you. You're grown men and women, and it's your life, and you know what you need to do or don't give a rip, and hopefully you do give a rip, or you wouldn't be in here, right? Okay, just really quick, when we talk about, and again, this is just kind of a review. Some of you's had physics, some of you haven't. That's okay. The world's not going to end. Some of you's had chemistry, and some of you haven't. Some of you probably had physical science in high school. But if you've had any of the sciences, most everyone should be familiar with some of our fundamental people of science, and I say fundamental, some of our forefathers of physics and chemistry. Of course, Newton probably had one of the greatest contributions to the scientific community ever until Einstein's theory of relativity. Okay, Newton, of course, you know this, created calculus. Is it Leipzig? Is the other guy's name that gets a little bit of credit for that too? But mostly Newton. He had to develop it to explain his three laws of motion. So you're pretty doggone sharp when you can do that. Of course, when you're not married and don't have kids and all you do is sit around and think, you got plenty of time. Okay. And there's other interesting things about Newton. I don't know if you know, he studied Bible prophecy. I don't know if you knew this, but he was big time into that. And he studied the heavens and the stars. And he tried to work out an equation for God, kind of like Einstein did, but he never did reach that point. But he was heavy into that, and he studied that, and of course the motions of the stars and the planets and eclipses, and we just had a solar eclipse, didn't we? That's pretty cool, wasn't it? It wasn't quite as dramatic as I was hoping it would be, but anyway, I guess you had to go to Cleveland, Tennessee, or Athens, Tennessee, or Nashville, Tennessee to get the totality, right? Okay, so we know there are great contributions today. Of course, Galileo before Newton, and Newton always gave Galileo basically a lot of credit for what he did. He made the comment, basically I'm standing on the shoulders of giants. Well, who was he talking about? Well, he's talking about Galileo. Those earlier scientists, Tycho Brahe, Galileo, Copernicus, you get back before Newton, they made a lot of major breakthroughs. You go back further than that, you go back to the Greeks. And most of you know, if you've had any philosophy, or not just philosophy, but science classes, the Greeks were heavy into science and mathematics. Many of the things that we know today were discovered over 2,000 years ago and had to be rediscovered. And it's sad that when the Library at Alexandria was destroyed, Lord knows what was lost. Lord knows where we would be technology-wise had that not been lost. So many of the things had to be rediscovered. And, those guys were sharp. Eratosthenes measured the circumference of the earth within I think 0.5% error. I mean, crazy stuff, y'all. And all he did was measure some angles and distances and use trig, basically. And, I mean, wow. I mean, he didn't have a calculator computer, graphing calculator, that flushed the toilets in China. No, he didn't have that, okay? So these guys, my wife made a comment last night. She said, where would America be, where would the world be were it not for America and all of our inventions? We invented everything. And I said, well, babe, not really. I said, a lot of inventions go to our credit, but I said, the reason it does is because all these Germans and these Swedes and these Englishmen and others, it wasn't just Germans and Swedes, but you find that chemistry, a lot of the chemistry you have today is thanks to a lot of German scientists back in the 1800s, especially organic chemistry. When you look at, Maxwell's equations, James Clerk Maxwell. Then you look at Michael Faraday. I mean, a lot of the things that were invented were built off of their principles that they discovered. So, yeah, we did invent a lot of stuff, but it was from these earlier people we built off their discoveries, okay? So that's a very quick review in science and the where it comes from. All right, now, and again, this, I know you say, why do you put that on there? Well, it never seems to fail that sometimes we students and teachers too, we don't follow a set of procedures when we problem solve. And this is very simple, but you always have to follow these steps to some degree in some order, maybe add a step here and there. But you always need to be able to identify, once you identify what's your variable, and that's the thing. What is the question telling me? I got to identify my variables, okay? Okay, what is velocity? What is acceleration? How do I know when I read this problem it's acceleration, okay? Well, hopefully you'll know that before you get out of here. Then you got to set it up again, equations. Everybody thinks, it never fails. You know, people say, well, yeah, boy, you got to be really good in math, don't you? Well, you got to be decent in math. I'll just confess, I'm not one of these. I never was a, super math genius, but I worked hard at it, and I still work hard at it, and I studied a lot. And when I got into physics, I realized a lot of this stuff they were teaching us math, how it applies. So, again, identifying equations, that's very important. And that seems to be some of our struggles, and again, it's a new vocabulary. This is really a new vocabulary. You know, you've had all these science classes, but you come to physics and it's kind of like, whoa, these are words I've never heard before. Applications maybe I haven't quite done before. And by the way, everything's built on physics. Believe it or not, everything. Chemistry too. Chemistry is built from physics. What do you think thermo is? When you take if you go on and do chemical engineering, you take P-Chem. Guess what that is? That's physics, the physics of chemistry. So everything, biology, meteorology, astronomy, geology, yes, geology is physics. What do you think those moving plates are? Well, there's forces involved, right? Okay. All right, then of course execute and evaluate. Again, how do I know I have the right answer? Well, you check yourself. You check your math, okay? And then of course evaluate. Now this is something you'll hear me say a lot. Does this make physical sense? If I say, all right, we're going to walk from here to the back wall, and it's about, I don't know, that's probably about 5 meters maybe, 4.5. Yeah, okay. And I'm going to say, all right, it takes me, and I'm just going to walk at a normal pace. All right. And then I record the time, and then I get an answer of like 25 meters per second. Does that make physical sense? Absolutely. I mean, you realize in 1 second that means I have to move 25 meters. I mean, we're talking $6 million man speed, right? Anybody ever seen the $6 million man? Y'all don't even know what I'm talking about. I watched every episode. You need to go Google it, all right? Lee Majors, he died here a while back. But yeah, no, it doesn't make any physical sense. So these are things, now I'm telling you, this can this can make you or break you. When you get an answer, you need to look at it. Does it make physical sense? Okay? I'm telling you. Because if you get something and it's a big number and it shouldn't be, you look at what you plugged in and wait a minute, something's not right. I mean, because it's physically impossible for me to move that fast. All right? Okay, let's move on. All right, now, of course, again, standard units, fundamental units. Why do we call them fundamental? Why don't we have volume up there? Why don't we have velocity up there? Why don't we have acceleration up there? Why don't we have force in newtons? Why don't we have momentum? Okay. All right. You're hitting around the ballpark. All right. Notice these quantities. All right. Length, time, and mass. What do we know about time? Very simple. What do we know about time? It's constant. It's always, and that's even probably debatable a little bit. It's always moving what? Absolutely. It's measurable, absolutely. And how do we define time? It's the forward flowing of events. Real simple. I like simple as much as possible, y'all. Okay? We don't need a PhD definition for everything. Okay? We just don't. Forward flowing of events. Yeah, sure is. Forward flowing of events is how you define time. Then you look at mass and you look at length. Well, length, notice length, if I say, all right, we're going to measure, oh, gummit, my meter stick disappeared. We're going to measure the length of this table. Well, I measure it in meters, don't I? Or centimeters or millimeters, whatever unit I'm going to use. That's not what I'm getting at, it's not a derived unit. It's not derived from another unit or from another formula. It's not derived. It's fundamental. And same thing for mass. Okay? And actually, we define mass as, there's actually your basic elementary definition, we say it's the amount of matter in an object, right? Okay, the amount of matter. Well, physically, that's not exactly, it is right, but it's more than that. We're actually, when you measure mass, you're actually measuring its resistance to change in motion, which is called inertia. Okay, so that's really what we're doing when we measure mass. We're not just, because how do you measure matter? And again, you say, well, the number of atoms, and well, that's true, but you got to realize something, because if I'm not careful, I'll be describing weight. And see, weight is affected by gravity, mass is not. Okay? Needless to say, the more mass you have, the greater resistance, right, to change in motion, right? A lot harder to move something that's very massive, isn't it? You have to have something typically very massive to move, right? For example, you don't go up and push a train, do you? But another train can. You see what I'm getting at? So you have to be careful sometimes when we look at how we define things. We tell you stuff, and then we come back later and say, well, we didn't really define it completely. Same thing in chemistry. We do that a lot in chemistry. All right, of course, hopefully you know by now meters, seconds, and meters is length, second is time, and mass in kilograms. But a lot of times we will use grams. But now, I'll say this. When we measure in here and we're doing Newton's laws, everything has to be in kilograms, okay? So it is the standard unit, the standard SI unit, okay? All right, now, again, I'm just going to go over this. I hope you know your SI prefixes by now. They are located, okay, they're not there. Yeah, very back of the book. I think you'll probably have to go to the appendices or additional resources on your e-text. Very back of the book, prefixes for powers of 10. Please be familiar with those and their symbols. Okay, now most of you probably already are. Most of you are, because you use them in chemistry some, but now we'll use, later on especially, in second semester, we'll be using them a lot. Okay? We'll be using them a lot. We're using some this semester, but we'll use them a lot next semester, okay? So just go ahead and familiarize yourself with those, okay? And I'm not going to give you a test on them for crying out loud, but just familiarize yourself with them, okay? All right, and then when we look at units and consistency, boy, Heidi, this is so important. And we take these simple things. You say, Miss Shields, this is simple stuff. I already know this. Well, good. But you'd be surprised at how, if we're not careful, we mess it up. Remember what I said a minute ago about the 25 meters per second if I walk at a steady pace from here to the back of the wall. You know, that's crazy, isn't it? Well, my units are right, but in reality, the reality of it is wrong. But what if I said, I took a measurement and I said it was 25 moles? Wait a minute. Something's not right there, is it? Moles is not how we measure distance and time, is it? No. No. That's a chemistry term. Right? So, dimensionally correct. That's what we mean by saying dimensionally correct. If I'm talking about, look y'all, if I'm talking about distance or displacement, let's just say displacement, then we should be in meters, shouldn't we? A unit of length, right? If I'm talking about volume, then it should be what? Meters cubed, centimeters cubed, milliliters, liters, and so on, right? If I'm talking about speed, and I'm getting a little ahead of myself, which is the rate of change in position, it should be meters per second, absolutely. If I'm talking about acceleration, should be meters per second squared, absolutely. So dimensionally correct. We want to keep our units consistent. If we have two different units and a problem, then guess what we're going to have to do? We've got to convert, don't we? You can't compare meters per second to centimeters per second. Not until you can't compare those values until you convert one to the other. Either convert everything to centimeters or convert everything to meters, right? Okay, I think that's self-explanatory. And then sig figs. And boy, I like the way they did this on this slide. They really summarize it, really just one page. Okay? Do you remember how to do significant figures? Remember that? Now, I'm not going to be a real stickler. Now, let me just say this. When you're taking these quizzes, pay close attention to how the question is formatted, and it might tell you to 3 significant figures. Or the answer may be out there, and it may have 3 placeholders. Well, that's 3 significant figures, okay? So be real careful when because sometimes you'll round, and it didn't want you to round, or maybe it wanted you to round to the nearest tenth. You round to the nearest tenth, and you put in the hundredth, and it'll count it wrong, even though you got it right. You follow me? So watch these questions when you take these quizzes, okay? So remember, sig figs, it's what? Multiply and divide, it's the lowest number of significant figures, period, right? If you're adding and subtracting, it's the lowest number to the right of the decimal, right? You remember that? Do I need to do that real quick? Everybody good with that? Yeah. Like 1.01 plus 1.215. All right, my final answer is going to be what? Well, this is 5, that's 2, that's 2, that's 2. But what am I going to do? Now, that 5 right there will make that 2 round up to 2.23, right? There's my final answer, right? Okay, you can do that, right? Okay. Now, let's look at pages, what did I say, 10 and 11? Instead of me just doing a bunch of typing and writing, I just want to talk a little bit about it. Orders of magnitude, okay? Orders of magnitude. Again, this is something you've probably done before and you just maybe didn't know it was called this. For example, if I say that for every 1 truckload of oranges, contains what? 105,600 oranges, right? 105,600. Okay? Let me simplify that a little bit. Let me say this. There we go. 100,600 oranges on a semi-trailer truckload of oranges. Okay? That many oranges. I'm just making that number up. So I could rightfully say then that on an order of a magnitude, every truckload of oranges, I know some of you are saying, dear God, we're going to have to look at this for 2 semesters, this kind of handwriting. Sorry. I'll try to be neat. Okay. It's on an order of magnitude of what? 1 times 10 to the 5th? Yeah. Right? That's all order of magnitude is. Yes. Yeah, you just round to the nearest power of 10. If you had 990, I don't know, lawnmowers, no, weed eaters. Let's say you had 990 weed eaters on a truck. You just say 1 to the 3rd, yeah, weed eaters. Okay, that's all order of magnitude. Why do we do that? Just to make general calculations, general assumptions. Okay. All right. Now, if you want to get into the specifics of doing a calculation, then you want to use the exact number, of course. But just to say, all right, they do this in businesses a lot when they're making parts. They say, okay, every crate has an order of magnitude of this many parts. Well, it might be a few off, but it's, again, just to kind of keep a general idea of what they're doing. Okay, and that's why we use it, just for general purposes to, instead of having to write really long numbers and the specifics of it, it's just for general purposes, okay? All right, scalar and vector. Now, come on, y'all. Surely the dear Lord, y'all can remember this. I know you're doing this in calculus. Scalar and vector. What is a scalar quantity? Single number only. Very easy. For example, 50 miles per hour. Scalar. Magnitude. Look, we look at the number. Magnitude only. Magnitude only. Vector quantity. 50 miles per hour south on 431. And if you're going that slow, you will get run over. because I hate that highway. 431 is a nightmare, isn't it? Especially on Fridays and Saturdays. And Sundays can be pretty bad, but now late afternoons every day is bad. But Saturdays and Sundays, Fridays and Saturday afternoons especially. Why? Because everybody's hitting the road. Work's over. All right. Okay? It's that simple. And you'll hear me say this a lot. Not every quantity we look at in here is a scalar quantity. Neither is every quantity we look at in here a vector quantity. Okay? For example, when we talk about speed, that's scalar. We talk about velocity, which has the same units, that's vector. Follow me? This is speed, and I'm getting a little ahead of myself. This is called velocity. It's also called acceleration because acceleration is derived from velocity. Okay? Right? Displacement is a vector quantity. Distance is a scalar quantity. Now, if I ask you how far is it to, or how long was your trip to Gulf Shores, down there and back, you tell me 700 miles. Okay? That's a scalar quantity. But if you give me directions, and actually you'd have to probably say it a little differently. Well, it's actually 350 miles south of here. That would be displacement, wouldn't it? Subtle changes there, okay? All right. Any questions on that? Okay? So, and again, what are some other vector quantities? Well, we said velocity, displacement, acceleration, force, momentum. What are some scalar quantities? Work. Work is a scalar quantity. Okay? We don't worry about the direction that the object is moving when work is being done on it. Now, I will say this, when we get into this, the direction at which we apply the force does matter, but again, it's the dot product. It's the scalar product. It's not the vector product, okay? And we'll get into that here in just a minute. And then we're going to look at some problems here. So when we draw vectors, y'all, again, I know this is review for most of you. Drawing a vector, we know we go from the tail to the tip. This, of course, is the tail, and this, of course, is the tip. And by the way, the length of the arrow gives us the magnitude. So if I'm drawing some vectors here, and I got one here, and then I've got one way over here, well, which one has the greatest magnitude, A or B? B. B, yeah. How do we know that? Well, look, from here to here. Notice it's a lot longer arrow, okay? The body of the arrow. All right? Notice this one's moving. This one, the direction's probably about what? 30 degrees. This one's probably what? To the 300 and, about through 330? Yeah, about 330. And you say, how do you measure that, Mr. Shields? You always measure counterclockwise from the positive x-axis. That is the best way to do it. Then that way you don't have to worry about, well, is it positive? Well, is it negative? If you'll do that every time, then you will not have to worry about the SIGN. Because when you put that in a calculator and you hit sine or cosine, guess what? It'll put the negative in there or the positive, right? It's the best way to do this, okay? I'm telling you, it's going to save you a lot of heartache. Just orient it from the positive x-axis counterclockwise. Always, okay? All right. Any questions on that? So direction, the body of the arrow is magnitude, direction is the tip, okay? All right? All right, any questions? Okay, now what about adding and subtracting vectors? Well, all of you have done this, and even multiplying. All right, if I take vector A, and then I take vector B, the resultant's going to be what? Okay, would that be A plus B? Could I rightfully say that and it be accurate? Absolutely. What if I did this? What if I come in here and say, here's A, and there's B. A little crooked there. It's supposed to be flat. Sorry. Then my resultant's going to be what? It's going to be A minus B, isn't it? And by the way, what would the value of that be? Positive or negative? It'd be negative, wouldn't it? Very good. Yeah. Yeah. Mm-hmm. B is much larger. Yeah. So we'll be going in the negative x direction, right? Okay. Okay? I mean, that's all we're doing, y'all. Now, you're going to hear me say this a lot. All right, we got to add vectors. Add vectors. We got to add the vectors. Add the vectors. Vectors add, you add add vectorially. When I say add vectorially, that's what we're doing. Okay? That's simple. What if I said we've got A, and then I want one that's 2A? Multiplying vectors. Well, that look about like twice. Could we say that's 2A? Close. Close counts in horseshoes, hand grenades, tornadoes, nuclear explosions, and Mr. Shields' class. And don't you ever forget it, all right? Don't you ever forget it. I'll just get it close, guys and gals. I'm not going to get a transient out and shoot points and get 10,000 magnification to make sure you use the right ink and pencil. Yes?
I had a question about sig figs. Is it all right if we use the capital E instead of the times 10?
You can, as far as on my, when you're giving me answers on the exam. Now on the, and that's a good question. On the mastering physics, sometimes I want to say it will want you to do the times 10. Sometimes it'll put out there in the answer blank, it'll go ahead and put the power number like times 10, but then you have to put in like positive or negative. Is it times 10 to the negative 10th or positive 10th or whatever? So you got, make sure you watch those answer blanks, because sometimes they'll get, you won't see it and you'll put the right answer in, but it will not be to the power of 10 they wanted it. So be careful. I'm glad you said that. But as far as me on the test, you can put the E and we're good. Yeah, I'm not too hard to please, okay? Yeah. Yeah, horseshoes, hand grenades, tornadoes, and nuclear explosions, especially close, does matter. Unfortunately, all right. We live in that age, y'all. Okay. All right, of course, now here is something you're going to hear me say a zillion times. We got to do the components. We got to find the components. We got to find the components. What the heck are the components? They are the parts that make up, they're the X and Y parts that make up the vector. It's that simple. Okay, that's all it is. You're going to hear me say this over and over and over and over and over and over and over. Okay? So what are we talking about? Notice, how do I find my Y component? A is the magnitude, look y'all, look right here. A is the magnitude of that vector. If I want to find what my Y component is of A, I've got to multiply times sine theta, right? If I want to find the X component of A, then I got to multiply times cosine theta. What does that basically do? It's basically giving me the what? The X and the Y? Right? Or the what? Calculus, folks? Okay? It's actually giving me the gummit. All right. I and the J parts, right? X and Y, I and J, right? Because remember, what is I and what is J? It's a unitless value, right? It's just telling us what direction it's in. I tells us it's in the X, J tells us it's in the Y. All right?
I don't know if I'm the only one, but that is the first time I've ever seen I coming.
Really?
Yes.
Okay.
Yeah.
Yeah, well, in Cal, probably should have written it this way. I mean, you can write it that way if you want to, but accurately written, I should have put the what? The cap on it. That better?
Okay, I understand what you're doing.
Okay.
That I've seen.
There, okay.
I just,
I and J, X and Y, yeah.
I'm used to that.
Yeah. The carrot cap, yeah. That's what we're talking about. Glad you mentioned that, because now it makes a little more sense maybe, okay? Yeah, I tells us it's in the X, J tells us in the Y, and Z is what? K? Yeah. We won't hardly ever use any K. We're going to probably do mostly two-dimensional. May do some three, but okay, we'll save you from K. Okay, huh? Yeah. Okay. For Cal, y'all doing some 3D?
Yeah.
Started it, yeah.
Yeah, we just learned all that today.
Yeah, well, good. All right, so this is all old hat to you, right? Most of you have seen this. It's old hat. I mean, I'm kind of like just, But I want to go over it, make sure we're on the same page. Now, look. Okay, Mr. Shields, what if I don't have the magnitude and I need to find the magnitude from my components? I do what is called the square root of these squares. Where does that come from? Pythagoras, yeah, absolutely. And then if I want to find my angle, how do I find my angle? I started to say I just found a boo, but there's tangent. We do arc-tangent, don't we? Inverse tangent, arctan. So when I want to find my angle, now y'all, I'm telling you, you're going to use this a bunch. A pretty good bit, okay? So I want to find my angle, then I do what? I do arctan, inverse tangent, what do you want to say? And then it's what? AY over AX. Now, do I have to have the A there? Again, it's just telling me this particular vector. It could be B, Y, BX, C, Y, C. It doesn't matter. It doesn't matter. Okay. Okay? I'm telling you, we're going to use that right there. Because when we start doing forces, or even velocities, and you got a velocity this way and a velocity that way. All right? The magnitude of this velocity is 20 meters per second. The magnitude of this velocity is 5 meters per second. What is the magnitude when you add those two vectors? What's the magnitude of those, or the resultant of those two vectors when you combine them? What will be the result of those two? Okay? And then at what angle will it be? Okay? All right. Okay, so again, what is this saying? The sum, now how do we find our x and how do we find our y? We add like terms. A little later on, we will have, we've got an object, the components of its motion is 5i minus 2j, and then the other object is moving at 2i plus 6j. All right, find the magnitude and the direction of that motion. Well, what do we have to do? We have to add like components. You add your j's, you add your i's together, do the square root of the squares, and then do arctan to find magnitude and direction. Okay? This gives us magnitude. Y'all, I'm telling you, this is an important slide. That gives you magnitude, and that gives you direction. Okay. All right. They tell you to refer to problem solving strategy 1.3. If you want to go back and look at that in your text, you can. Okay. All right. Okay. And again, unit vector notation, y'all. Do I really need to go over this? I mean, y'all have done this. Y'all are doing this right now. Okay. Unit vector I corresponds with X, and J with Y, and K with Z, right? So we can express any vector that way. Okay? And there's your little carrot cap. Okay? Okay? That's how we can express vectors. We can leave it in the X, or we can do IJK. You know, X, Y, Z, IJK. Okay? All right. All right, any questions? Again, old hat, right? Doing it right now in calculus, which is perfect timing. I know used to we kind of were out of sync, and it wasn't nobody's fault. It's just the way it was set up with the way the students took their calculuses. But now we've got it past several years. We've had it synced right, and so it's a lot better. Okay. All right. Scalar product, the dot product. Okay. I don't know if you've gotten to this yet. Have y'all done the scalar product? I can't remember. I was thinking you should have. You should have already done the dot product. Again, what is this? This is just to find the what? Now notice right here. We want to find the magnitude of a particular vector. Okay? So, I want to find this right here. Right? Doesn't matter which part we choose. Notice how they change the orientation. Notice they're doing it tail to tail. Typically we write vectors this way, don't we? Head to tail, right? Well, you don't have to. You can do tail to tail. right? Have you ever seen vectors written tail to tail? Most of the time you may see it that way, but you can write it head to tail. All right, let me say this, and you've probably already been told this, but I'm going to tell you again. If you haven't, you're fixing to hear it. As long as we keep, this is common sense, the magnitude and direction of the vector the same, it doesn't matter how we orient it. How the vectors are oriented. Okay? Doesn't matter. Doesn't matter. So in other words, look. All right, let me erase a little bit here. If I come in here and do this right here. If I come in here and say, okay, we got a vector this way, and then quit. And then it goes over this way. Well, I can rewrite it and do this. Right? Did I change the direction? No. Did I change the magnitude? No. I just shifted it around. And let me say this. Sometimes it's better to do that. Sometimes it's better to do that. To go ahead and redraw it. You notice I did my Cartesian coordinates, my graph. I hope you do a lot of that, because if you just get on here and start and try to work a problem, no, I'm going to frown, okay? And I'm going to tell you right now, your engineering professors are really going to frown. They are going to scream at you, you better draw that free body diagram and you better label it. I got a cousin, second or third cousin. He's up in his 80s now. Dude's a genius, and PhD in engineering, taught at Florida State forever, professor emeritus. He's got a resume a mile long, and he's a Sneed student, Sneed grad, graduated in the early 50s from Sneed. Went on to Alabama, got out early at Alabama, went to Oklahoma State, got his PhD in engineering. And he always told me, he said, whatever you do, he said, you make your kids draw those free body diagrams. He said, because any engineering problem in the world, any engineering problem you'll ever be faced with can be solved from that free body diagram. That's what he told me. And he knows, okay? I mean, he was doing stuff for the government way back when. He even told me he was on the team that helped develop what we now call the internet. So, yeah, I think he knows what he's talking about. He said, oh yeah, he said, back in the 60s, we had it, our campus hooked up, and we were some of the first people to do the research into that and develop it. Crazy stuff. Robert Braswell's his name. If you want to go Google him on the internet and look up his page, it's like a mile long. I mean, it's just all the different stuff he's done. So he knows what he's talking about. All right, so we have what is called the scalar product, which is what we were just looking at there. And by the way, there's an equation that you might want to use. We will use that some, but really what we'll end up doing, we'll use the scalar product, but some, again, that's just to find the magnitude of that, the dot product of those vectors. And then we have, and again, this is just showing you it doesn't, again, it can be, and by the way, it can be negative and it can be zero. Okay? Now remember, what does the negative tell us? That it changed direction or it's in the other direction. For example, if I'm walking along here and I'm moving east and then I stop and turn around and go west, I changed direction, didn't I? Well, guess what? My sign on my value has to represent that. Okay? It has to represent that because there was a change in direction. All right? Okay, then we have what is called, of course, this is calculating the scalar product using components. Now look, basically what we're looking at here is there are two different ways to come to the same answer. We can do AB cosine theta, or we can do by adding the terms together, multiplying the terms together and then adding them up, right? We can do it one of two ways. I don't care. It doesn't matter. This is just showing you another way to do the same thing. Okay?
Matter what the stuff the problem gives us, which one will be easier to do.
Yeah. Well, it really doesn't matter. Yeah. Yeah. Really doesn't matter. Just another way to do the same thing. Okay? And then, of course, the vector product, or what we call the cross product. Now, where do we use the cross product? We're not going to use it so much this semester as we will next semester. Where can we use you could use a cross product, but it's easier just to do, I say we won't use it. We will use it this semester, but it really comes into play next semester when we deal with magnetic fields. Okay? Magnetic fields. Because it's the cross product. Okay? It's the cross product. All right? Okay. And that's how we can find vector product. Notice it's AB, and notice it's the magnitudes of AB. And then the angle. Now notice, what if B is in the opposite direction? Okay? What if you got A times B, but then you have A times negative B? Okay? We're going to have a change in direction, right? It's going to change direction. Okay? All right. But that's how we do the vector product. Okay? All right. And I think that is about it. Yeah.